Okay, hey guys, welcome. So to the recitation, we will be solving some problems in combinatorics. I believe I sent you the list of the problems that we're going to solve today. So let's get started. Most of these problems rely on the pigeonhole principle. So let me start with problem one. Problem one, did you guys did you try any of these problems like during the reading time? Which problem did you try to solve? Hmm? Yeah, that's a good activity. Well, wait, Abby. You were cooking some problem or you're actually cooking? Anyway, let's start with problem one. All right, problem one says the following. If I have 7 numbers, let's say x1, x2, x5, x7, sorry. Let's say that these are real numbers. And we have to show that there exists there are two of them, not one, geez. Ij such that, well, Ij from 1 to 7, okay, let me be specific here. 1 to 7, such that this inequality holds true. Xi minus xj over 1 plus xi xj. This is less or equal than 1 over square root of 3. Okay, so that was the problem. As you can see, I have 7 numbers and I have to show that there exist 2 indices, 2 of them from those 7 numbers, xi, xj, such that that quantity in absolute value is less or equal than 1 over square root of 3. This actually does this ring a bell to you when you look at it? Does that expression in the absolute value remind you of anything? Like, for example, I don't know, there is some trigonometric identity that you learn probably somewhere. So, so maybe the idea maybe the fraction xi minus xj over 1 plus xi xj, maybe this fraction reminds us of some trigonometric identity involving one of the trigonometric functions. And let me be more specific here, such as maybe this one here. Let me show it to you. Tangent of x minus y is something like tangent of x minus tangent of y, everything over 1 plus tangent of x tangent of y. So you see, when we have this identity here, maybe we can do something about it. Maybe we'll try to make that fraction over there look like this one, right? Okay, so now let's get started. And what we're going to do is the following. So Now let's try to transfer some of these, to transfer these problem or into from an algebraic one to make it look like into a trigonometric one. So that's what we're trying to do. And now we're doing the following. For each, let's say, I, between 1 and 7, there exists a theta I, right? So we're trying to make this correspondence somehow from this interval, let's say negative pi over 2, pi over 2, such that xi is tangent of theta I, right? And now, once we have this, right, now we're doing the following. So the trick is to divide now, divide the interval negative pi over 2, pi over 2. Since I have 7 numbers, it will be ideal for me to divide this interval into how many subintervals? Because I have in mind to apply the pigeonhole principle, right? And
so 7 or 6, right?
6, exactly. So I need to divide this interval into 6 subintervals, but not just any subintervals. What kind of subintervals should I divide them into? Of equal length. This is important. So this is of equal length. So these intervals need to be distanced equally. So how should I distance them equally? So from negative pi over 2 to 0, right, which is 3 pi over 2, 0. So I should divide this, you see, I have 2 quadrants here, the fourth one and the first one, right, negative pi over 2, pi over 2. Or you can look at this as 3 pi over 2 to 0, and then from 0 to pi over 2. Just imagine 0 from pi over 2 can be divided. So let's divide this. So how should we divide of equal length? In fact, can you tell me without even writing the subintervals, what will be the length of each subinterval of those 6? So that is a question. What is the length of that? So how far they're distance from their end points? So if you pick one of those subintervals, what will be the length? So let's see. Okay, let me give you a hint. Only if you look at, for example, if we look at, let's say, okay, only one part, right? 0 pi over 2. And I want to divide this into 3 equal parts. How should I divide this? So it will be from 0, we have 3 subintervals. Of equal length. And that would be, those would be what?
In between 0 to pi over 2.
Yes.
So
but
0 to pi over 4 and then pi over 4 to pi over 2.
Try something, if you have, imagine that you must get 3 of them, not just 2. So if you go from 0 to pi over 4 and then pi over 4 to pi over 2, you only have 2 and they're equally distant, right?
0 to pi over 6.
Exactly.
Pi over
so
6 to pi over 3 and pi over 3 to pi over 2.
Exactly. So 0 to pi over 6, pi over 6 to, you just divide by 6, for example, pi over 3, and then pi over 3 pi over 2. You see, the length of these three intervals is pi over 6, correct? Right? So pi over 3 minus pi over 6 is pi over 6. Pi over 2 minus pi over 3 is pi over 6. Well, you can do the same thing from similarly. One can do the same for the interval let's say 3 pi over 2, right? You could divide it by 6 again. Okay, you divide by, yes, you divide this into 3 subintervals of equal length. In any case, the length of, so I have 6 intervals, right? And I have 7 numbers. And keep in mind that my numbers now are tangent of, my numbers will be some numbers between negative pi over 2 and pi over 2, and I have 7 of them. So this will imply what by the pigeonhole principle? By the pigeonhole principle, this implies what? So I have 6 intervals, 7 numbers. This will imply that 2 of them will be in one of the subintervals, right? There exists, let's say, exist I and j such that what? Such that, let's say, theta, and I have these numbers, right, let's call them theta 1, theta 7. Let's say I have 2 of them in one of the subintervals. And the distance between these two will be at most pi over 6, which is less than pi over 6, right? Well, let's put less or equal. So now applying the tangent function, this implies that tangent of, let's say, an absolute value of theta I minus theta j is less or equal than tangent of pi over 6. Well, we also know that tangent in this interval is increasing. That's why we pick these negative, the fourth and the first quadrant. And now this guy will be tangent of pi over 6 is nothing else than just 1 over square root of 3. Okay, great. But this guy, but tangent of theta I, and now I'm going back to the identity that I just mentioned at the beginning, tangent of theta I minus theta j is this guy, it's tangent of theta I minus tangent of theta j over 1 plus tangent of theta I tangent of theta j. And there we go, right? And we said at the beginning that you'll see there exists a theta I such that xi is tangent of the theta I. So we had our algebraic problem, and we transferred it into a trigonometric problem, and that's it. We're done. It was tricky, I admit. This could be like a Putnam B2, maybe B3, depends. A1, A2, A3, or B1, or B2, B3, something like this. Is this clear for everybody? Okay, now let me do the problem number 2. So problem 2 says the following. So, wait, what does it say? So we had these 9 points. the statement was, let there be given 9 points, 9 lattice points. This is important, right? Keep in mind that these lattice points are points of integer coordinates with integral coordinates. What I mean by that is that both coordinates, the x and y coordinates, are integers with integral coordinates, okay? Right? Okay. We have this in the 3-dimensional Euclidean space. Okay. And then it says that show that there is a lattice point on the interior of one of the line segments joining 2 of these points, joining 2 of these points. All right, this was a Putnam, Putnam, what year was it? A1, 1971. All right, this is a very nice problem, even for cooking. So keep in mind, we have 9 lattice points in the 3-dimensional Euclidean space. So what do you need to do? What do you think? So you need to divide them somehow into how many categories of points? Let me put it this way. In such a way you can have 2 of them will...
It needs to be 8, right?
Exactly. So you need to divide these 9 points into 8 categories of points, such that 2 of them, by the Pigeonhole Principle, such that 2 of them will lie in the same category. So how you should categorize? That's the question now. How you should categorize these points, these 8 points, and these points, right? These 9 points. So you need to put them in 8 categories. So let me be more specific. Well, let me put it this way. The set of all lattice points, keep in mind that they're lattice points. This is important. Can be divided into 8 classes, let's say. And how we should divide this? And I'm going to be, so I will divide this in the following way, in 8 classes according to the parity, of the coordinates. Keep in mind, this is how we divide it. So what kind of points do I have? So I can have, let's say, I have a point, let's say A1 of, pay attention, they're in 3-dimensional space. So how many coordinates do they have? 3, right? Remember from calculus 3, when you have a point in the three-dimensional space, it has three coordinates. So you can have, for example, and the parities are 2. So you have odd and even, correct? So you'll have, let's say, well, odd. This will be odd, odd, odd. Let's say the second point can be odd, odd, even. Let's say another one, third one. So you have only 8 categories if you look at it. Let's say odd, even, even. A4 will be, what do we have? Odd, even, even. Even, even, even. You have another one, A5, like even, even, odd. Then A6 could be something like this, even, odd, odd. And 2 more. So what are we missing here? Even, odd, even. And the other one, 8, will be what? So odd, even, even, we said. Odd, even, odd. Do we have this? Odd, even, even. Odd, even, odd. Yeah. All right. So these are the 8 points, 8 classes of points, right? Or maybe I shouldn't have put here like A1, A2, maybe, but that would be confusing. So that would be class, not actually no. Okay. Well, let me denote these are the classes. In fact, why not? These are not the points, right? These are the classes. You have the class A1 of points, which have coordinates odd, 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 even, and so on. There are 8 classes. So these are the 8 classes of points. Of lattice points. Okay. Since we have 9 points, this will imply what? By the pigeonhole principle? This implies what? That by the pigeonhole principle, there exist, let's say, 2 points, P and Q. And let's notice, okay, let me say specifically, there exist 2 points, P and Q, such that they belong to the same class. Right? Agree with me? Okay. So they belong to one of these class. So what should I do now? Because look at what my statement wants from me. Keep in mind that the line segment joining these 2 points is a lattice point. Keep in mind this. There is a lattice point of the line segment joining these 2 points. So now I have 2 points P and Q if one of these classes. So what should I do about this? So take the midpoint, right? Because the midpoint will always be, so now the midpoint because they're in the same class, pay attention. It's not like one point P will be in the class A1 and 1.2 will be in the class of A2. Pay attention, that's not going to happen because, okay, let me take the midpoint of the line segment. PQ, right? Since P and Q, okay, let me, okay, this is a lattice point. This is a lattice point. Wait, this is a, yes. It is a lattice point. Keep in mind that the coordinates of the, you know, the coordinates you just divide by 2, each coordinate. Okay. So this is a lattice point, we're done. That's it. Let me be clear here. Look at these classes of points. These are the classes A1, A2, A3, and A, all the way to A8. These are not points. You see, P and Q will belong to the same class. P and Q will be in one of these 8. Will be in A1, A2, or A8. And if you take, imagine that P has coordinates odd, 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 and Q will have the same, odd, odd, odd. So you divide by 2, odd plus odd will be even, divided by 2, there you go. The same thing will happen. Or if you pick, for example, in A5, but you have to pick them in the same class, right? Same category of lattice points. You cannot pick P from A1 and Q from, I don't know, A8, because it's, right, they belong to the same class. You see, I have 9 points, 8 classes. I divided them into 8 classes by the pigeonhole principle. There exist 2 of these points lying in the same class. That's it. You take the midpoint and there you go. That was the trick. Anyway, that was problem number 2. And now problem number 3. Again, this was problem 3 was an easy one. And it says the following: let A be any set of 20 integers distinct integers. Let me be, okay, chosen from the arithmetic progression um, 1, 4, 7, and we go all the way to 100. Now we're asked to show that there must be two distinct integers in A whose sum is 104. Okay, let me just close the door. So all right, so let's look at this problem. Did you try it? So I have 20 distinct integers. That's a very important information. And they're chosen from this, from this arithmetic progression. And I need to find 2 distinct of them, and with their sum to be 104. Right. So what should we do here? So we should divide this set, right? Imagine that we have this set. Maybe we should divide it, or so consider a partition, and the following partition of the set. So we're given this set. So let's write it again. So it's 1, 4, 7, and 100. And what kind of partition should we consider, given the fact that the sum is, you have to show that there exists two of them with their sum 104? Well, it's quite clear what kind of partition. So we're considering the following partition. Let's take the first element to be 1. So let's leave the endpoints, the first one and the last one, let's leave them aside. In fact, I'm going to do the following. 1. Then I'm going to take this set with two elements, 4 and 100. Then 7 with 97. So now I'm just going to group them together, right? Because you have how many pairs? You have, anyway, let's group them. Now you have what? 10 and 94. And you keep going. And let's see, the last one, I'm going to leave 49 and 52 and 55, sorry. And the last one will be 52. I'm going to leave these guys alone. So you see 1 and 52, I'm going to leave them as singletons, right? So the singletons, these are the set that contain only 1 point. All right.
I have a question, just a curious one.
Yeah.
So, like, I see you had, like, you grouped 4 and 100. How come you didn't do, like, group 1 and 100, and then it would be 4 and 97?
Because their sum is not 104.
Oh, the sum's 1 and 4. Okay.
Yeah. So if I would have asked you to show that there exist two distinct integers in A such that their sum was 101, then you have said, like, okay, maybe I should have grouped 97 and 4.
Mm-hmm. I understand. Yes.
So that's why you group them together. The sum of these, in fact, maybe I should say, yeah, let's say, the sum of the elements from all, and I'm going to be clear here, non-singleton. So in this way, I'm excluding these two. So this guy and this guy, these are singletons. And the same goes for this guy, right? Okay, so the sum of the elements from all non-singleton sets in the partition is 104. Well, that's obvious, right? Keep in mind that this is what we have to show. Look here. So that's okay. All right, and let's see. How many sets are there? That is the first question. How many sets are in the partition? If you look at them, how many of them are there? 15? Nah, not quite. Try more. you also add those two as well. So it goes from 3 to 3, so all the way to 52. Well, how many of them are there? A little bit more than 15, there are 18. There are 18 of them. So these 18 sets, okay, let me be here. There are 18 sets in the partition. That's important. All right, let's see, what do we have? We have 18 sets, and let's see what we, and I have, okay, and I have 20 distinct integers. So I have these 20 distinct integers, and somehow I put them into this in these 18 sets. What can you tell me? And pay attention, look at this. So I'm choosing A to be any set of 20 distinct integers. So this will imply what? Since A contains 20 distinct elements, integers, right? What can we say by the pigeonhole principle? By the pigeonhole principle, I always forget to write the O. By the pigeonhole principle, what do we get?
At least one of them has to have multiple elements, like multiple of the elements, because
Exactly.
and because there's two more, either we have two of them with 2 elements, or we have one with 3.
Exactly, right? All right, so let's write this. So by the pigeonhole principle, it follows that it must be the case that sum, let's say, and when I say this sum, I'll be specific, well, at least 2, right? Sets in this partition, in the above partition. You see, you have to write everything in words here when you solve a combinatorics problem, so that things will be even clearer. So at least 2 sets in the above partition, right, must contain two elements from A, right? And if you look the sum of these 2 elements from A, it will always be 104, right? And the sum of these elements and the sum of these elements is 104. And that's it. You see, that was a trick, to partition that set into sets of 2 elements. Well, I can complicate this problem immediately. What if I'm looking at another? Try to invent similar problems. For example, try to look at maybe not 2 of them, maybe 3 of them, and I can pick a larger one. So you have to divide in 3. The partition has to contain sets with 3 numbers and so on. So you can play around with it. You can just try to go from the solution to the statement. So you can play around with these. Anyway, oh my God. Let me do one more problem. Wow. So problem number 5, I think. This was again a Putnam problem. And it says the following: prove that, this was a bit tricky, I admit. Prove that, actually I thought of it for a long time. Prove that for every set X, containing these numbers, x1, xn, of n real numbers, there exists a non-empty subset S of X. Is also very ambiguous, right? It's very vague. It's not ambiguous, vague. It's not, doesn't give you too many details. So you have to of X and an integer M such that we have the following inequality: M plus the sum of all these elements S in S is less or equal than 1 over n plus 1. Wow, look at it. Okay, and let me give you briefly the solution since I'm running a bit over time. Well. You see, the problem is that you need to start from somewhere. That is the problem with this problem. So where to start from? And when you look at the statement, you don't get too many ideas. But if you have the idea, then you can go from there. So you need to start from some. So let me say that this was a Putnam B2 in 2006. I admit it was a bit tricky, but anyway. So you need to start from somewhere. And you need to make things as small as possible. And for example, when you think of some real numbers, maybe you think of some intervals. Maybe you're trying to divide those intervals into something. For example, let me put it this way. So this problem rings a bell. It's very similar to the following one. And let me tell you the following one, which is pretty straightforward. So suppose I have n plus 1 numbers, all of them in this interval, closed interval 0, 1. Show that there exist 2 of them such that their difference is less than 1 over n, right? So I have n plus 1 in the interval 0, 1. And then I have, then I'm asked to show that there exist 2 of them, at least 2 of them, such that their difference is at most 1 over n. Well, that's easy. You just divide. That's why, because this 1 over n plus 1 brings me to that problem for some reason. So I have to, and maybe I should look at the solution of that problem. And for the solution for that problem is pretty straightforward. So you divide the interval 0, 1 into 0, 1 over n, 1 over n, 2 over n, and so on, into n subintervals of equal length. Well, since there are n plus 1 numbers, at least 2 of them will fall into one of those subintervals, and the difference between those is at most 1 over n. So maybe I should cook up something which will be similar to that, and it's a bit okay. So it's a bit, so let me do it this way. so I'm going to use a fractional part, and you'll see why. So because since I have a real number x, what is that thing that will allow me to go from any real number to the interval 0, 1, let's say? Well, it's the fractional part. So let x be the fractional part. So this will be x minus the integer part of x. So this will be the fractional part of x. Because this has an amazing property that the fractional part will always be, you see, any number has its integer part and its fractional part. So this fractional part will always be between 0 and 1. So this fractional part belongs to this interval 0, closed and open at 1, right? And now what I'm going to do is the following. So because I'm trying to construct this set somehow. So for I, going from 0 all the way to n, we put si to be the sum of these. So it will be x1 plus xi. Okay? And now we're going to take the fractional part of these numbers. So now take the fractional part of these numbers of si. So the fractional part of s0, fractional part of s1, and we're going all the way to fractional part of sn. And keep in mind that there are n plus 1 of them, and they belong to the interval 0, 1. But I don't know what is the order between them. I don't know if the fractional part of s0 is less or greater than the fractional part of s1. So I need to sort them somehow. So what I'm going to do, and sort them, and let's say sort them such that we obtain the following numbers. So instead of these, I'll call them t0 less than or equal than t1 less or equal than tn, right? And of course, these are between 0 and 1. Keep that in mind, right? Less or equal than 0 here, because of this guy here. Okay, so I sorted my numbers like this between 0 and 1. And now, of course, I'm going to apply the principle that I just explained at the beginning. So I have n plus 1 numbers, all of them in so now let's look at the difference. Well, I have n plus 1 numbers in the intervals 0, 1, right? This implies, so how should I phrase this? Okay, I'm going to be specific. So now the difference is, that's a nice modification of the problem that I just stated at the beginning. So now the difference is, let's say t0 minus 0, which is t0, t1 minus t0, and we're going all the way to, let's say tn minus 1, right? These differences add up to 1. Okay, well, guess what? They add up to 1 if I divide my intervals into n equal parts. So now dividing, so applying the problem that I just said at the beginning, dividing the interval 0, 1 into n equal parts. Let's say, you understand, into n subintervals of equal length, that's what I mean. By the pigeonhole principle, it follows that that one of these differences let's say t0 minus 0, which is t0, t1 minus t0, T2 minus T1 and so on, Tn minus Tn minus 1 is less or equal than 1 over n plus 1, right? Well, I divide this into n plus 1 equal parts. And well, one of these differences, and it equals, keep in mind that these T i's are the fractional part. So it equals, let's say plus minus, I don't know exactly which one, the fractional part of Si, right? Minus the fractional part of Sj, something like this, right? For some 0 less than I, less than j, and less than n. Okay? And now we will put this, we'll construct the set. Now put S to be the set of these. Let's take Si plus 1 and all the way to Sj. And M, we'll take the difference of their integer part. So the integer part of Si minus the integer part of Sj. And then, well, we need to verify the inequality, then M plus the sum of all S in S. This will be nothing else than just M plus the sum of all these. If you look at them, it will be nothing else than just Sj minus Si. And this will be nothing else than just the absolute value of the fractional part of Sj minus the fractional part of Si. And of course, this will be less or equal than 1 over n plus 1. Yeah, that's a bit tricky, I would say. And that's it. So this is how you construct the set. Okay, I'm gonna stop here. They were a bit tricky, I admit, the problems. But yeah, I think you got the main idea. I had one more problem, in fact, 2 more problems to discuss. Unfortunately, well, I didn't have time. And since I see some of my Calc 1 students here, I'll stop here. Thank you very much. And I'll be back in a couple of minutes.
I see you, Cezar.